In the mathematical discipline of linear algebra, a matrix decomposition or matrix factorization is a factorization of a matrix into a product of matrices. There are many different matrix decompositions, each finds use among a particular class of problems. Example: in numerical analysis, different decompositions are used to implement efficient matrix algorithms. For instance, when solving a system of linear equations, the matrix A can be decomposed via the LU decomposition. The LU decomposition factorizes a matrix into a lower triangular matrix L and an upper triangular matrix U. The systems and require fewer additions and multiplications to solve, compared with the original system, though one might require significantly more digits in inexact arithmetic such as floating point. Similarly, the QR decomposition expresses A as QR with Q an orthogonal matrix and R an upper triangular matrix. The system Q equals B is solved by Rx equals QT B equals C, and the system Rx equals C is solved by back substitution. The number of additions and multiplications required is about twice that of using the LU solver, but no more digits are required in inexact arithmetic because the QR decomposition is numerically stable. Decompositions related to solving systems of linear equations. LU decomposition applicable to square matrix A. Decomposition, where L is lower triangular and U is upper triangular. Related. The LDU decomposition is, where L is lower triangular with ones on the diagonal, U is upper triangular with ones on the diagonal, and D is a diagonal matrix. Related. The LUP decomposition is, where L is lower triangular, U is upper triangular, and P is a permutation matrix. Existence. An LUP decomposition exists for any square matrix A. When P is an identity matrix, the LUP decomposition reduces to the LU decomposition. If the LU decomposition exists, the LDU decomposition does too. Comments. The LUP and LU decompositions are useful in solving an n by n system of linear equations. These decompositions summarize the process of Gaussian elimination in matrix form. Matrix P represents any row interchanges carried out in the process of Gaussian elimination. If Gaussian elimination produces the row echelon form without requiring any row interchanges, then P equals I, so and LU decomposition exists. LU reduction block LU decomposition rank factorization applicable to M by N matrix A of rank R. Decomposition, where C is an M by R full column rank matrix and F is an R by N full row rank matrix. Comment. The rank factorization can be used to compute the Moore-Penrose pseudo-inverse of A, which one can apply to obtain all solutions of the linear system. Cholesky decomposition applicable to square, symmetric, positive definite matrix A. Decomposition, where U is upper triangular with positive diagonal entries. Comment. The Cholesky decomposition is unique. Comment. The Cholesky decomposition is also applicable for complex Hermitian positive definite matrices. Comment. An alternative is the LDL decomposition, which can avoid extracting square roots. QR decomposition applicable to M by N matrix A. Decomposition, where Q is an orthogonal matrix of size M by M, and R is an upper triangular matrix of size M by N. Comment. The QR decomposition provides an alternative way of solving the system of equations without inverting the matrix A. The fact that Q is orthogonal means that, so that is equivalent to, which is easier to solve since R is triangular. RQR factorization interpolative decomposition decompositions based on eigenvalues and related concepts. Eigen decomposition, also called spectral decomposition, applicable to square matrix A with distinct eigenvectors. Decomposition, where D is a diagonal matrix formed from the eigenvalues of A, and the columns of V are the corresponding eigenvectors of A. Existence. An n by n matrix A always has n eigenvalues. which can be ordered to form an n by n diagonal matrix D and a corresponding matrix of non-zero columns V that satisfies the eigenvalue equation. If the n eigenvectors are distinct, then V is invertible, implying the decomposition. Comment. One can always normalize the eigenvectors to have length 1. If is real symmetric, is always invertible and can be made to have normalized columns, then the equation holds because each eigenvector is orthogonal to the other. Therefore, the decomposition reads as comment. The condition of having n distinct eigenvalues is sufficient, but not necessary. The necessary and sufficient condition is for each eigenvalue to have geometric multiplicity equal to its algebraic multiplicity. Comment. For example, the difference equation starting from the initial condition is solved by, which is equivalent to, where V and D are the matrices formed from the eigenvectors and eigenvalues of A. Since D is diagonal, raising it to power just involves raising each element on the diagonal to the power t. This is much easier to do and to understand than raising A to power t, since A is usually not diagonal. Jordan decomposition. The Jordan normal form and the Jordan-Chevalier decomposition applicable to square matrix A. Comment. The Jordan normal form generalizes the eigendecomposition to cases where there are repeated eigenvalues and cannot be diagonalized. The Jordan-Chevalier decomposition does this without choosing a basis. Schur decomposition applicable to square matrix A. Comment. There are two versions of this decomposition: the complex Schur decomposition and the real Schur decomposition. A complex matrix always has a complex Schur decomposition. Decomposition, where U is a unitary matrix, is the conjugate transpose of U, and T is an upper triangular matrix called the complex Schur form, which has the eigenvalues of A along its diagonal. Decomposition, where A, V, S and are matrices that contain real numbers only. In this case, V is an orthogonal matrix, is the transpose of E, and S is a block upper triangular matrix called the real Schur form. The blocks on the diagonal of S are of size 1 times 1 or 2 times 2. QZ decomposition, also called generalized Schur decomposition, applicable to square matrices A and B. Comment. There are two versions of this decomposition: complex and real decomposition, and where Q and Z are unitary matrices, the H superscript represents conjugate transpose, and S and T are upper triangular matrices. Comment. In the complex QZ decomposition, the ratios of the diagonal elements of S to the corresponding diagonal elements of T are the generalized eigenvalues that solve the generalized eigenvalue problem. Decomposition, and where A, B, Q, Z, S, and T are matrices containing real numbers only. In this case Q and Z are orthogonal matrices, the T superscript represents transposition, and S and T are block upper triangular matrices. The blocks on the diagonal of S and T are of size 1 times 1 or 2 times 2. Takagi's factorization applicable to square, complex, symmetric matrix A. Decomposition, where D is a real non-negative diagonal matrix, and V is unitary, denotes the matrix transpose of E. Comment. The diagonal elements of D are the non-negative square roots of the eigenvalues of comment. V may be complex even if A is real. Comment. This is not a special case of the eigendecomposition. Singular value decomposition applicable to M by N matrix A. Decomposition, where D is a non-negative diagonal matrix, and U and V are unitary matrices, and denotes the conjugate transpose of E. Comment. The diagonal elements of D are called the singular values of A. Comment. Like the eigendecomposition above, the singular value decomposition involves finding basis directions along which matrix multiplication is equivalent to scalar multiplication. But it has greater generality since the matrix under consideration need not be square. Other decompositions Polar decomposition applicable to square, complex, matrix A. Decomposition, where U is a unitary matrix and P is a positive semi-definite Hermitian matrix. Algebraic polar decomposition applicable to square, complex, non-singular matrix A. Decomposition, where Q is a complex orthogonal matrix and S is complex symmetric matrix. Comment. The existence of this decomposition is equivalent to being similar to Sinkhorn normal form applicable to square real matrix A with strictly positive elements. Decomposition, where S is doubly stochastic and D1 and D2 are real diagonal matrices with strictly positive elements. Sectoral decomposition applicable to square, complex matrix A with numerical range contained in the sector. Decomposition, where C is an invertible complex matrix and with all generalizations. There exist analogues of the SVD, QR, Liu and Cholesky factorizations for Cauchy matrices and C matrices or continuous matrices. A quasi-matrix is, like a matrix, a rectangular scheme whose elements are indexed, but one discrete index is replaced by a continuous index. Likewise, a C-matrix is continuous in both indices. As an example of a C-matrix, one can think of the kernel of an integral operator. These factorizations are based on early work by Fredholm, Hilbert and Schmidt. For an account, and a translation to English of the seminal papers, see Stewart.